afternoon, everyone. I'm Moukhik Misra. My paper title is Diabetes Prediction and Analysis Using Machine Learning, a Comparative Study. So the co-authors are Mohit Sosaria and Professor Jayakumar K. and I'm a third-year BTech student at VIT Vellore. So we'll just go on. So basically, as we all know, diabetes is quite a chronic and widespread disease that's usually caused by the lack of insulin production or improper utilization of insulin, which is produced by the pancreas. It's a disease which usually affects middle-aged to elderly people. However, it's possible that this disease affects younger people due to lifestyle or genetic reasons. So in our study, we've considered type 2 diabetes. There are two types of diabetes, so type 1 and type 2. We've considered type 2 diabetes. So the blood glucose level rises, which leads to health problems. Diabetes is usually an incurable disease, but an early and precise detection of diabetes allows potential patients or people at risk to change their lifestyle and take precautions which can significantly reduce the risk associated with diabetes. But one problem we encountered while obtaining the dataset is that there's quite a significant scarcity of labeled dataset that properly capture outliers present in the diabetes data. So for our study, we've used the PIMA Indians dataset. It contains lots of features such as age, glucose, BMI, blood pressure, insulin, pregnancies, and history as well. So we'll be using this dataset to predict the occurrence of diabetes in patients. So our methodology basically follows pre-processing, exploratory data analysis, then followed by data partitioning, data standardization, and then model implementation. Our model implementation consists of 4 parts. We've used 4 techniques, namely logistic regression, k-nearest neighbors, light gradient boosting machine, and ensemble technique, which uses both KNN and light gradient boosting machine. I'll be talking about the implementation soon. So here we can see the proposed system flowchart and architecture for our proposed system of proposed models. So basically, we first start with importing our data, then a pre-processing stage, which is our custom medium imputation to handle the imbalanced data set and the outliers, followed by we've conducted extensive visualizations for all the data pre and post the pre-processing stages. So, and then we find the correlation and the interrelation between the class and between healthy and diabetic patients, and then perform data partitioning and data standardization using standard scalar, and followed by implementation of models, and then performance evaluation using standard metrics such as accuracy, precision, recall, and ROC-AUC score, and so on. So I'll just be going over the methodology now. So first is our pre-processing stage. So in pre-processing, we've implemented a custom median imputation method where since in the dataset, it contained a lot of zero values, which should not be there. So we counted all those zero values and then we replaced them with not a number, so it wouldn't affect our median calculations. Then we calculated the median based on whether the patient is healthy or diabetic to get a general overview. Now, since we have this new median value, we have now replaced the not a number values with the calculated median values based on healthy and diabetic patients. So this allows us to deal with the outliers and gives us a better distribution of the data as well. Next stage, we've performed visualizations for the pre-imputation and post-median imputation, and as well as plotted healthy and diabetic entries separately. We can see the mean, the histograms, and all those kind of things. Next, for better balancing of data and for better performance of the models, we've employed data partitioning technique where we created 15 custom partitions of the data based on healthy and diabetic. So we've got a lot of numeric and categorical columns. So we're combining 2 numerical columns together, 2 categorical columns together, and finding the relationship between them, and then creating 15 such partitions. Next, all the numeric columns are standardized using standard scalar, and we encode all the labels into numeric form using label encoder. Finally, a correlation plot is created to find the correlation between all the created partitions and the original features that were given. So next we come to the model implementation part. 4 models, as I mentioned before: logistic regression, k-nearest neighbors, light gradient boosting machine, and an ensemble learning technique, which uses both light gradient boosting machine and KNN. For hyperparameter optimization, we've used grid search cross-validation for 3 of the methods, while for light gradient boosting machine, we've used random search technique. I'll come to why we've used random search a little later. So we've used soft voting classifier by giving equal weight to both the LGBM and the KNN models. Performance evaluation is done using metrics such as precision, accuracy, recall, F1 score, and ROC AUC score. All these are tabulated, and visualizations such as the precision recall graph, the ROC curve, and confusion matrix have been provided as well. Next, we'll come to our results that we've obtained. So as you can see, here are cross-validation results for the 5 folds. Each cross-validation we performed 5 times for all of the particular models. You get our accuracy, precision, recall, F1 score, ROC, AUC. We've done the same for the light gradient boosting machine and the ensemble technique. This is the standard visualization for our bar graphs and for all the results that we've obtained. So you have a confusion matrix, you have your ROC curves, you have your PR curve, and you have standard metrics which you can obtain from the confusion matrix. Next, I'll move on to performance comparison. So this is our accuracy comparison. We've performed comparisons between the accuracy, precision, recall, and F1 score of the implemented models. The general trend that we find is that the KNN model performs the worst, while the ensemble method gives us the best possible metrics in all calculations. So here are accuracy, here's our precision, here's our recall, and here's our F1 score comparison. Next, as I mentioned before, we used grid search hyperparameter optimization. We have for logistic regression, which sets C value and penalty. So we can find we find that 1.0 C value and a penalty of L2, which is the rich penalty, is the best possible, is the most optimal, gives us the best accuracy. Then for KNN, we find that the number of neighbors is 9. So the reason that we use randomized search for light gradient boosting machine is to limit the number of iterations that you have. Since light gradient boosting machine, we've used a number of hyperparameters, and we've defined a huge set of hyperparameters and values. It would lead to a lot of combinations that could be made. So now, to limit those combinations, we've used randomized search and we've limited it to 300 iterations or 300 different combinations of hyperparameters. So that's how we've obtained the light gradient boosting machine, and ensemble techniques we've also obtained using grid search. All the performance metrics that were obtained before, we've just tabulated here. One discrepancy that we found is that ROC and AUC, that the light gradient boosting machine beats out the ensemble technique in the ROC AUC metric. A reason for that is due to the fact the data set is quite imbalanced, and hence the ROC AUC does not actually provide a good metric standard for imbalanced data set. Hence, this explains the discrepancy that we found there. So as a result, the results that we've obtained are that KNN model, that we've implemented 4 models. So LR, KNN, LGBM, and ensemble. We've used grid search and randomized search hyperparameter optimization for 5 cross validations. And the mean accuracy that we obtained for the KNN model is 80.6%. For the logistic regression model, we've obtained a mean accuracy of 83.2%. For the light gradient boosting machine, we've obtained an mean accuracy of 88.8%. So the best possible accuracy that we've obtained from our ensemble technique is 89.45%. So this generally follows the consistent trend that we've seen. As I explained before, just in the ROC AUC metric is where the LGBM beats the ensemble model due to the imbalance in the data set. So I'd just like to conclude by saying that we've performed analysis and multiple visualizations, as well as given a custom median imputation technique for pre-processing of the data. We've obtained good accuracies on prediction, especially on the ensemble technique. For future work, we're planning to explore more ML algorithms and looking at their effect on this particular data set. We're also planning to create more accurate, trying to create more accurate ensemble methods. And we're also planning to consider better feature extraction techniques in the future. Thank you.
Thank you for your wonderful